So yeah, let's get back to the things that we have discussed before. So last time, while we started the discussion for the diffusion models from like DDPM, DDIM, like school-based model kind of things, and we actually realized that actually all the things that we are learning, basically representing with the training of the diffusion model is that basically it's all about like expressing the mapping from the data distribution to the latent distribution using the SDE formulation, right? So we could say that actually both the fold process and the reverse process can be represented as the stochastic differential equation, especially when you define the fold SDE into this form. We could say that the reverse SDE also can be defined in this way with this core function here. And then what we also have seen is that actually it turns out that we can find the corresponding ODE formulation that basically matches the marginal distribution, which means that by simply solving the ODE formulation, now we can do both ways of the mapping, right? So that was the basic idea for the diffusion models. So after we see this, now we can see that like everything, the mapping can be basically, considered as basically the ODE formulation. So this was the PFODE. And the thing is that when we discussed the PFODE, we did not see the details in terms of like how we exactly can derive this formulation from either the fold SD and the reverse SD, right? I just said that like this is the PFODE, right? I didn't say like how we can derive this. I'm not gonna get into all the details for that. If you are interested in basically how we can derive like this formulation, I strongly recommend you check out this paper and see how we can do this. But the very high level kind of thing is that basically to derive those kind of things, we need to start to discuss this formulation first. This is the very basic formulation, which is called the Fokker-Planck equation, which is basically showing some kind of the relationship between the SD formulation and the probability for the intermediate data point of the XT. So this is the formulation that shows the relationship between these two. And from this, then we can consider basically deriving all the things for the PFOD, but we are not going to get into all the details because it will take another like 1 hour. But yeah, please keep this in mind because like this is also the formulation that we're going to keep seeing for the rest of the part of the course. So this was kind of the basic idea. And after we start to see the ODE formulation, what we can see is that now we can consider making some kind of some dedicated ODE solver based on the structure of the formulation. So the idea that we have seen the DPM solver case was basically actually this is like one of the specific example in terms of like trying to basically make some kind of the analytic solutions for the ODE, while it's impossible to make some kind of the fully analytic solution for the entire ODE. But here what we tried to do was basically integrating at least like the linear part analytically and doing some kind of the better approximation for the non-linear part of the integration. So in terms of that, we could say that we can achieve some kind of the better results even with the few step. So also, especially the interesting part of the DPM solver was that if we take the first order approximation for those like non-linear parts, then it became exactly the same with the DDIM, right? So we could see that like why DDIM performs better, the non-stochastic version performs better with the fewer number of steps because it's kind of some first order approximation for the ODE formulation, right? And we could go further, which means that we could basically do the higher order the approximation for the nonlinear part in terms of that we can achieve some kind of the better results with the even fewer the number of the steps. So I guess some of you might now try to implement the higher order DPM solver in terms of like reducing the number of the steps in your code, but we'll see. So that's kind of the basic idea. So this is the basically figure that I have shown from the very beginning of like this course. Basically, the advantages of the diffusion model is that you can achieve the high quality outputs without any kind of mode collapse issues. Basically, the limitation is all about the speed, right? So what we have discussed from the previous lectures is like all about how we are going to produce the quality outputs with the fewer the number of the steps. So we started from the DDPM, which required like more or less like typically people use the 1,000 time steps, right? And then we reduce that into the more or less the 50 to the 200 using the DDIM. And by seeing that the DDIM can be seen as kind of the first order approximation of the ODE deformulation, when we have some the higher order resolution, now we could reduce the number of the time steps into the 10 to the 15. So that's really kind of the remarkable progress in terms like reducing the competition from the 1,000 to the 10, right? 100 times of kind of improvement, right? But the question is that how can you also improve further? So if you see the quite recent, the image or the video generated models, you can see that their degeneration speed is really fast. Actually, the very latest degeneration models for the image and the videos are just requiring really few steps, 1 to 5 kind of steps, which means that they did something, right? It's not just using those kind of the ideas. So actually, there are tons of the ideas in terms of how we can further accelerate the diffusion process in the degeneration. The thing is that what we have seen is in these like the previous lectures are basically all the ideas that we can directly apply in the test time. So that is also a very interesting point of the diffusion models in terms of that. You don't need to retrain the model. Using some kind of the pre-trained model, by simply changing the formulations of degeneration, you can achieve this level of the acceleration, almost like 100 times of the acceleration. That was the very interesting point, right? But also the idea is that some kind of recent ideas are basically also about like how we can achieve the further the acceleration with some kind of the fine tuning. So that's also kind of the ideas, which is the ideas is called the distillation. So given some kind of the pre-trained model, you do some kind of the fine tuning of the neural network in a way that now we can make it as kind of the like one-step generation the model. So you can basically get some kind of the outputs with some kind of the single step the computation. So for that, so we are not gonna get into too much details for the many acceleration techniques. But the reason that I'm just mentioning this is that one of the kind of biggest motivation of discussing the flow models that we are going to start to discuss from today is also about the acceleration with some kind of fine tuning. So that's kind of the reason that I'm just mentioning this. But this is really important topic in terms of that we can further reduce the computation. The most representative idea for the fine-tuning based kind of the acceleration is the consistency models. So we are not going to get into any details for this, but here the basic idea for this kind of the technique is that you first basically compute ODE, which means that you from some kind of the noise samples, the standard Gaussian sample, you perform the ODE solver all the way that you get some kind of the realistic data point here, right? So which means that you have some kind of the trajectory from the standard Gaussian sample to the data point there, right? So here the basic idea is that we do some kind of a noise prediction in every single point, right? And we also have seen that the noise prediction can be used to compute the expected final value using the Tweedie's formula, right? So actually, we can see that the role of the neural net is actually to predict the final output, the expectation for the final output, right? So the basic idea for the constant model is that for all the points along the way of this trajectory, we want to basically foresee the final outputs from the earlier stage of the trajectory. So the basic idea is that we make the expectation of the final output in the earlier point here to be close to the expectation of the final output in the later point here. So we already know that this kind of trajectory, we already computed the ODE here. For the earlier point here, the xt prime here, when you see the expectation of the final output, we make it to get closer to the expectation of the final output, the next point. So that's kind of the basic idea. Obviously, there are lots of the details in terms of how we can make this kind of training to be more stable. There are some kind of the details. You can also check out the details in the paper. But without seeing those kind of details, with the relatively simple idea in terms having some kind of the earlier stage of some kind of the forecasting for the final outputs, we can achieve some kind of the results in terms like making some realistic the outputs, even with the very few number of steps, even the one or the two steps. So that's kind of the good idea for the consensus models. And not only for this, there are lots of some kind of similar ideas in terms of like, accelerating degeneration. But the kind of the downside for all those kind of the ideas is that they are all requiring some kind of pre-trained diffusion models, and starting from that for the fine tuning. So that's the kind of the idea. So which means that by spending more time in the training the phase, you can basically reduce the computation in the test time. So that's kind of the basic idea for those kind of the acceleration techniques. So even without like having any understanding for all the details here, now at least you can see some kind of the history of like the literature in terms of like how the techniques have been evolved over time. In terms of that we started from the DDPM 1000 steps and the DDIM 200 steps and DPM solvers and many other dedicated OD solvers like going down to the 10 steps, and then consistency models or some kind of other acceleration techniques, which also goes down to the 1 or the 2 steps, while requiring the distillation, the technique with some kind of pre-trained models. So those are some kind of some picture in terms of that, how we can do some kind of accelerations with the diffusion models. So the thing is that any other options is like all the kind of things that we can do. So from today, actually, we are going to discuss completely different degenerate model, which is the flow matching. But after discussing all the things, actually, you realize that while the idea for the flow matching stems from the completely different kind of literature, the root, eventually, actually, that becomes kind of the identical with the diffusion models. So that's also kind of the very interesting point. While it might be quite painful in terms like seeing some kind of the connections between these two. So we're gonna get into that. So so as kind of another idea in terms of making some acceleration, and actually as kind of the completely new idea of degenerate models. So we are going to start to discuss the flow models. The thing is that in the context of the diffusion models, here the key thing is that, so please keep this in mind. So this is the really important point, and this is really confusing point. In the diffusion model context, we have seen the time range, the time domain, from the perspective of the flow, the fold process, right? So the time t is starting from 0, from the data distribution, and through the fold diffusion process, we are mapping the x0 all the way to the x capital T here, right? So starting from the data distribution x0, and then going to the x capital T, right? So that was kind of the convention that we used in the diffusion models. The thing is that, so it's always good to basically keep all the kind of the notations here. But the problem is that for the flow matching the context, as I said, this is completely new general model, which is coming from the completely new some kind of the literature and the root, basically. And they are seeing basically this kind of the time domain from the generation perspective. So which means that now the x0 starts from the something kind of the known distribution, which is typically standard Gaussian distribution in our case, and then which is now mapped to the one of the data point sample from the data distribution to the x1. So we're gonna switch the range, flipping the time range. Starting from the data distribution to the Gaussian distribution. Now we go into this way, the Gaussian distribution to the data distribution. So now this will be x0 and this will be x1. Okay. You're gonna see that actually this is very confusing. Even I get confused with this kind of the changes of the notations. Sorry about that. But I also had some kind of the thoughts in terms like, what if we just like follow like one of those things for the discussion for everything? The thing is that all the materials that you can see for the diffusion models basically follow those notations, and all the kind of the materials for the flow matching follows basically the time range. So that's kind of the confusing point. So we're gonna switch from this to this in the discussion for the flow models. X basically 1 means the Taylor distribution, and X0 basically means the sample from the Gaussian distribution. Make sense? Starting from the X0 to the X1, that's the reverse process. Don't get confused. So keep this in mind, and so based on that, let's discuss the flow matching. So basically, you're gonna see that like all the discussion for the every distribution model is kind of the same. We basically set the sort of the reference distribution, which is typically the central Gaussian distribution, and the Taylor distribution, which is the P1 here. I'm not gonna get into too much details for this for now, but actually the key distinction between the flow models and the diffusion models is that all the things that we discussed for the diffusion model is assuming that this reference distribution is the standard Gaussian distribution, right? If we change this into another distribution, actually we have seen that example in our test, right? Not having the reference distribution as the standard, the isotropic distribution for some kind of anisotropic distribution, right? But if we change this like reference distribution into the very new kind of distribution in the diffusion models, then everything will be changed. So that will be quite complicated. The good thing of the flow model is that we can make this to be really anything. Even when you basically make this like reference distribution to any other distribution, the formulation is not changed at all. So that's also kind of the very interesting point of the flow models. You can see it's kind of a generalization, right? So that's kind of thing. But in any case, like we're gonna basically set the reference distribution as the P0 and the Taylor distribution is the P1. And then we're gonna basically introduce some kind of the new terms, which is something that we already have seen. We are just like having some kind of names for that. Basically, we're gonna define the function pi, which is the flow map. So flow map is basically representing the trajectory starting from the point x here. So when you have the basically pi tx here, basically the input here becomes the sample from the reference distribution, typically the P0. So the input to this function should be x0, basically a sample from the reference distribution, and the pi t basically means some kind of the point over the trajectory at the time step t. So we already start from the x0, we change the time range, and then going to the x1, right? And pi t is basically representing that the trajectory. So there is no stochasticity here. Everything is, this is another basically ODE-based kind of business models, which means that zero stochasticity, okay? So which means that if you basically determine the starting point x0, then all the points along the trajectory will be determined, right? Which means that we can now define some kind of function for that. So basically the xt starting from the specific the x0 will be denoted as the pi t x0. So that's the kind of the new notations. And the vector field. So basically this is the ODE-based kind of the formulations. We're gonna also basically define the vector field, which is basically defined based on our flow map, right? So you can see that basically how the vector field and the flow map will be related to each other. Obviously, when you define the ODE formulation based on the vector field, that will basically compute the flow map at every time step t. So that's kind of basic thing. So this is nothing but we already have seen that the flow map here can be basically defined based on this ODE formulation with the vector field here. So obviously, the starting point of the trajectory should be the same with like this point, right? By definition of the flow map. So we are defining the flow map as kind of trajectory starting from this. So when the time t here is basically 0, it should be basically the same the x0, right? And if we basically map the x0 all the way to the time 1 here, then there should be one of the sample of the data distribution. Okay? Yeah, so that's the thing. So every kind of like the single point over the trajectory basically can be computed by solving the ODE like this. Starting from the x0, basically integrating the vector field over the time t. So that's kind of thing. So I'm going to sometimes abuse some kind of notations in terms of like having the xt here, which is kind of using some kind of things, but the notations, but indicating the point at the time step t starting from the x0. Okay? So that's the thing. And then in the diffusion model, the context, we have seen some kind of the probability distribution for the noisy data point, right? So in the score-based models, we had that the reference distribution and the data distribution, and then the probability distribution for the intermediate, the noisy data point xt. Do you remember how we defined this? The data distribution for the intermediate, the noisy data point. How did we define for this score-based model in the Langevin dynamics? Like what we have seen is basically having some kind of the Gaussian convolution for every single the data point, the samples of the data distribution, right? So the thing is that we don't have any closed formulation for this. That's why we do all the things, right? We only have the samples of the data distribution. And then to perform the Langevin dynamics, basically what we have seen last time for the score-based model is that we are defining the probability distribution for the intermediate, the noisy data point, the xt, as kind of the Gaussian convolution for each of these single data point, right? So this is basically the same thing. Basically, the probability distribution for the intermediate data point of the xt, for the intermediate time step, the t here, we're gonna just have the name for that in the construct flow the matching, which is called the probability density path or the probability path. So those are some kind of the new name for like those things. So please keep these three things in mind. We're gonna keep discussing those three things. We're gonna have the flow map, which can be computed by the vector field, right? So if we have this, then we can compute this. If we have this, and we can also compute this. And based on this, we can also compute the probability path as well, the things. So the thing is that in the diffusion models, for the score-based models, what we have seen is that actually we are defining this first, right? We defined like this, the probability distribution for the intermediate data point by basically injecting some kind of the Gaussian noise, doing some kind of Gaussian deconvolution, right? And based on that, we can basically formulate all the fold and the reversible processes. And then based on that, we can compute the ODE formulation using the PFODE, which means that now we can compute the vector field from the probability path that we define, right? The thing is that in the flow dematching, we're gonna go in a kind of the reverse way. We're gonna basically first define the vector field and the flow map, and based on that, how we're gonna see how this probability path is also basically defined based on like this too. So there are some kind of connections in that way. So here, basically, the thing is that it's kind of like more straightforward in terms of like how the vector field and the flow map, these two are basically related to each other, right? Basically, this can be computed by solving the ODE from the vector field, right? But the thing is that it's not very clear, how exactly this one is basically related with these two. So that's kind of some complicated part. We are not gonna get into deep of that. But this is like the part that this equation comes out again. And so this is like the equation that we can see some kind of connections like between these two. So while this looks quite complicated, the good thing is that if we ignore these parts, if we see some kind of very simple ODE formulation, ignore this part, because like if we see that this is actually the kind of the ODE formulation of the vector field, right? So if we ignore this part, then actually this f function can be considered as kind of our vector field. As you can see in here. So very simplified version, right? So when there's no stochasticity, the f function becomes of the vector field, then we can see some kind of the very simple, some kind of connection between the probability path, which is basically the probability distribution for the data point at the time step t, and also the vector field here. So actually, this formulation showing the relationship between the vector field and the probability distribution is one of the kind of key things to see, to derive the PFODE from the Fokker-Planck equation, but we are not going to get into all the details for that. But this is kind of thing. So now we can see how exactly the vector field is basically related with the probability path. So based on that, what we can do is that with some kind of the derivation here, once we basically have any kind of the vector field here, based on that, for any of the data point over the trajectory, we can compute the log probability. So now the vector field can be used to compute like how likely each of the data point will be there at the time step t. So that's kind of the key things here. So basically this means that if we can somehow find a vector field that can maximizes the log probability here for each of the data sample that we have. So X1, so don't get confused. The X1 is the data sample, not the Gaussian sample, okay? We are going from the X0 to the X1. X0 is the Gaussian sample and X1 is the data sample, right? So for the X1, if we can now compute the log probability for each of the data point, right? Using the vector field that we have. So if we can somehow find a vector field that maximizes the log probability for all the data points, which means that now we found a kind of the good mapping, right? That's kind of the mapping that we can basically map the X0 into the X1. So which means that somehow if we can find this kind of the vector field, this is kind of the information. This is kind of the function that basically encodes some kind of the information for the mapping. So which means that as we also have done similarly in the diffusion models, we can try to basically memorize this information of the vector field that encodes this like mapping information using the neural net. For each of the sample of the time t and also the sample of the xt, we can consider basically training a neural net that can basically predict this kind of the velocity. And that's kind of similar with like what we have seen for the diffusion model case, right? So as we basically trained the noise predictor in the diffusion models, somehow if we can have some the information for the vector field, we can consider training a neural net that basically encodes all those kind of the vector field information, which is maximizing the log probability for the X1, right? Then based on that, as we have seen in the previous slide, we can compute the ODE that will become our degeneration in the process. So that's kind of the high level idea in terms of how we can also define another type of the ODE based degenerate model by directly defining the flow map, also the vector field, before we get into some specific definitions for the probability path. But obviously here the question is that how we can find such kind of vector field, right? So when you start from any kind of X0 and then sending that into the X1 using the vector field, that should be one of the realistic data point, right? So the question is that how we can find such kind of the vector field that maximizes the log probability for all the X1. So that's kind of thing. One doable way is that we actually define the loss function as the log probability that we have seen in the previous slide. So when you define the log probability like this, for any point of the X1, the sample, the data point, that we basically actually go all the way back, running the ODE in the backwards in terms of going into the X0 here. Then now we can compute this log probability by computing this, right? Basically, this means that from the X1, we train the neural net over time in a way that we have the vector field. Using the vector field, we go in the backward all the way to the X0 here and compute the probability in this way. And basically, we are finding the vector field in a way that we maximizes this. Okay, so this is kind of doable with the formulations here. But yeah, okay, so it is clear for each of the data point. Lots of the data point X1 that we have, actually, starting from the arbitrary vector field, we perform the ODE in the backward. It's kind of the fold process in the diffusion model case, and then having the backward trajectory. And based on that, we compute the log probability by computing this. In a way that we find some kind of the better vector field that maximizes this. So that's kind of the very early version of the idea in terms of like, how we can, make some kind of degenerate model by directly learning the vector field here. So this is really different with like what we have seen in the diffusion model case, right? In the diffusion model case, we somehow defined the probability path, the conditional probability path actually, that we're going to also see it in the next slide. And based on that, we could derive all the things of this kind of ODE formulation, which is giving us the vector field here, right? But here, we don't define any kind of the probability path and directly somehow try to find the vector field here in terms of like maximizing this. Obviously, the conclusion that I'm going to say is that this is not working that well. So we're gonna see like how we can make it to be similar to the diffusion model of the case in a way that we can make it more retractable in terms of training. But can you see like what's the problem like this? If we train the vector field, the velocity prediction network in this way, what would be kind of the issue? You can really implement this, right? But what would be kind of issue with this? I mean, the issue all comes from basically solving the ODE, right? Solving the ODE in a like very stable way is super challenging, unless we have some very specific form of the ODE formulation. But for those kind of general form, the problem is that, the ODE solve basically can be not only computationally expensive, but also numerically unstable. So that's kind of the issue. So the thing is that if you train the neural net in this way, then every time when you compute the loss function, you need to compute the ODE, right? And then the backpropagation should be done all the way through the ODE, the solve, right? But the ODE, the solve is basically computationally expensive and also can be numerically unstable. So that's kind of the problems. So here the question is that how we can basically learn those kind of the vector field without basically making our the loss function to involve some kind of the ODE, the solve. So that's kind of the basic idea here. Okay. But is it clear? But can you see that how we are basically evolving kind of things in terms of that we started from the DDPM, DDIM things and then see how those kind of like mapping can be defined as kind of the SD formulation and also the ODE formulation. And then now we are kind of going the other way around. Now we are going to basically define this mapping directly as kind of the ODE formulation in a way that how actually we are going the reverse way. Now we define the mapping as kind of the vector field, and from this we're gonna see how those are basically related with the probability paths and those things. So that's kind of another interesting idea. So let's try to basically make the vector field the learning without basically solving the ODE for the loss function computation. So from this point, we're gonna start to see that actually what we are discussing in this kind of the new general model becomes slightly, actually kind of getting quite similar with diffusion models, but having some quite different some kind of the explanation for that. So what we are going to do is that what we need is basically this, right? Probability the path for the time step t. But instead of like directly seeing that, we are going to consider all the things which is called the conditional things, the conditional the probability path, conditional flow map, and also the conditional the vector field. See, here basically the conditional the probability path basically means that when we assume that the data distribution is basically a simple the Gaussian distribution which is centered at the x1 and also the very small deviance here. So can you actually see that this is something that we already have seen in the previous lecture? Something familiar? No? So this might be confusing because we changed the time, the range, and also some of the notations here. But actually what we are doing here is exactly the same that we have done in the score-based model. You can say that, what's that? Yeah. So we are basically doing some kind of the Gaussian convolution for each of the data point of the x1, right? So in a way that we define some kind of the noisy the probability distribution of the time step t. So this is exactly the same thing. Basically, having some kind of the Gaussian this kind of convolution with some kind of by seeing that each of the point as kind of the data point as kind of some small Gaussians here. So that's kind of thing. So for this conditional setup, that basically what we are going to see is that now we are going to assume that given any kind of sample of the x1, we are going to assume that the data distribution is given as kind of the very small Gaussian centered at the specific point of the x1. In a way that we're gonna get back to the probability path of the pt, the marginal, the conditional, the path by taking the integral in this way. So that's basically what we are going to do. So as I said, you can see that this like the conditional setup as kind of the case that the reference distribution is exactly the same, while basically we are sort of seeing the data distribution as kind of some concentrated the Gaussian centered at given the point of the x1 here. So the reason why we are having this kind of conditional setup is that the good thing is that now our data distribution became Gaussian distribution again. Which we know the analytic form. So once we have some kind of the analytic form for the data distribution, then we can derive the analytic form for the flow map and also the vector field as well. So all the computation becomes like more tractable and feasible. And after seeing all the things for the conditional setup, we're gonna see basically how we can compute the marginal, the probability path, and also the marginal vector field based on those kind of conditional things. So that's the basic idea. So that's kind of thing. So basically, when you see the conditional probability path like this thing, so don't confuse again. X1 is the data point, right? From the X1, given kind of the X1, what be kind of the conditional probability path for the time step t, right? So you can see this is kind of similar with the fold process of diffusion models. In the fold process, we have seen that how we can basically inject some kind of the Gaussian noise with some kind of the drift for each of the data point of the x1, right? So this is actually kind of like corresponds to the fold jump distribution in the diffusion model case. So we have seen the bunch of things, right? For the VP case and the VE case, those are defined in this way. So this formulation may look quite different with the VP case, but the reason for that is that we changed the time, the range. So that's kind of the problem, right? But this is kind of something that we have also seen in the diffusion model case, the fold jump distribution, which was basically adding some kind of Gaussian noise into the x1, right? So now we can see some kind of connections between the flow model and the diffusion models. And as I said, we're gonna keep seeing these kind of those like three things: flow map, vector field, and the probability path, and see basically how those are basically related to each other. That's also what we have seen in the previous slide. And then we can also see the same thing. For the conditional setup, we're going to also see the conditional flow map, conditional vector field, and the conditional probability path. And the thing is that in the diffusion model case, we started to define this one, right? EDPM, we are defining the fold jump, and based on that, all the other things are defined, right? Defining this first and deriving all the other things. What we are going to do here is that we are going to define this first. We're going to first define the flow map into this simple linear function first, and see how the other things are basically derived based on that. So you can see how we are basically generalize this kind of the idea in terms of expanding our scope, in terms of like having some specific, in the previously diffusion models, we had some specific form of like those things, especially the VP formulation or the VE formulation, and extending this into the other things. And now we want to basically like expand our scope in terms of like, what if we first define the conditional flow map, and based on that, define all the other things. So that's kind of the case. So don't also get confused. So this is the conditional setup, so conditioned by the realistic, the data point, x1 here. And then the flow map always basically takes some kind of the starting point as the input. The starting point is typically the Gaussian distribution, but as I said in the flow model, it does not need to be Gaussian. But basically, a sample from the starting distribution, the reference distribution, And this is basically the sample that we are taking as the condition of the data point, right? Then from the definition of like this, you can see, right? I mean, so basically if this t is 0 here, what should be output like this? I mean, very simple question, right? It should be x0, right? By our the definition of the conditional the flow map. So basically the definition of the flow map is that the trajectory over the space starting from the x0, right? So if the t is 0, then this should be obviously x0, right? But this is also conditionally the setup that we are assuming the data distribution is very tiny Gaussian centered x1, right? Then what should be the output when the t is 1? It should be close to the x1, right? Because that's basically only because the sample of the data distribution, right? So obviously from this kind of the conditioning the setup, if we specify the x0 and the x1, when the t is 0, then the output should be x0. And the t is 1, that should be very close to the x1, right? Which means that while we see some kind of the general form of the still some linear function of the conditional the flow map, our definition of like these function and these function should satisfy those kind of the boundary condition. You can define whatever sigma here and the mu here. It's okay. We also have seen many generalizations in the diffusion model case, right? So we're gonna also see some multiple options defining like those two terms, right? Actually, you can literally define any things. But whatever you define for these two things, the thing is that when the time t is 0, then the output should be x0. And when the time t is 1, then the output should be close to the x1. You need to define these two in that way, right? And now you want to say that this is something that is getting closer to something that you already have seen. The problem 5 of the test was kind of getting close to this, right? So that's kind of the things that you guys basically seeing some kind of connection between the diffusion models and the flow mapping. So with this kind of like the linear function, you're gonna see those kind of some straight trajectory from the any of the x0 here mapping to the x1 here. So having some kind of the straight trajectories. So the reason like why we are having this kind of like simple form, the linear function of the conditional flow map is that based on that, so once we define the conditional flow map into this very simple way, obviously there should be some ways, reasons for that, right? The reason for like defining the conditional flow map in this like simple way is that then now everything becomes quite simple. And then we can easily define that the corresponding the conditional property path also can be defined into the Gaussian distribution. We have seen the relationship between the flow map, the vector field and the flow map, and also the vector field and the property path, right? In the previous slides. And based on that, if you derive all the things, then you're gonna see that from the linear, the condition flow map, actually the conditional the property path given the x1 actually becomes the simple the Gaussian the form. This is also very similar with like what we have seen, right? Basically our variational diffusion model was defined in this way with some kind of the conditions for the SNR for those two functions, right? So while we are also using another new notations like the mu and the sigma, you can get the sense of like those things will be somehow identical with some kind of the functions that we have seen in the previous lectures. So sorry for that, we just keep using some kind of new notations because of those are coming from the different literature. But you can see like these are kind of actually related with some of the terms in the variational diffusion models. So as I said, you need to have those kind of conditions in terms of that we need to satisfy the boundary condition that the time step is 0, the output should be x0, and the input is 1, and it should be the Gaussian distribution. So that's the thing. So yeah, so basically with this kind of like the boundary, the boundary condition, you're gonna see that when the time t is 0, that becomes like this, and the time 1 is that, then we get this, right? So then based on that, let's check this out. So you can just try this yourself, like doing some kind of a sanity check. So given this kind of like the condition flow map, the linear function, with those kind of some boundary conditions, just like put those things and check what you get here. So based on this kind of simplest, the option for the mu and the sigma function, if we derive the conditional probability path and the conditional flow map and the conditional vector field, then you're gonna see that we get this form, right? This is also quite obvious, right? With that kind of the simple form, obviously the conditional flow map should be interpolation between these 2 points, making straight trajectory from the x0 to the x1. Right? Makes sense, right? And also the probability path is defined in that way, and also the vector field is defined as kind of the vector on that in the straight line. That's very obvious, right? So this is kind of the lesson for now. You don't need to take a photo. I'm gonna update the slides. But this is kind of the lesson here is in terms of that. Now we can make some kind of the new ODE-based degenerate model by first defining some kind of the conditional flow map, and everything can be derived based on that. In the context of like making defining some trajectories, the conditional trajectory to first, the conditional trajectories do not need to be any kind of some fancy like complex kind of things. Even the simplest one would be okay. But also the option is that what if we really follow the things that we have seen in the diffusion model case? In the diffusion model case, we first defined the conditional probability path into this way. Right? This is the VP case, having some kind of the shift and also basically injecting some kind of noise, right? So the conditional probability path was basically defined as kind of some fold the jump distribution, right? Having some kind of the Gaussian distribution. And from this, obviously, we can derive the other things as well. So based on that, the conditional probability path, now we're going to see that the vector field is computed in this way. So while we're going to discuss also the merger case as well, the thing is that we are basically seeing some kind of the conditional, some sort of these core terms in the diffusion case, which is basically used for some kind of a long-term dynamics kind of process, right? But we now switch everything is kind of the ODE formulation, but instead of this core function, now we are seeing some kind of the vector field. And obviously these two will be somehow related to each other, right? We're gonna get into this connection between these two next time. But we are basically seeing some kind of the other types of the quantity, which is now the vector field. And based on that, we can define the ODE formulation and we can perform basically the degeneration process. And if we also compare this kind of the conditional flow matching with the previous case, everything was the marginal setup in the previous case. Obviously, there's no closed form for anything, for any of the vector field, all the things. So we needed to basically learn the vector field with some kind of the very expensive, the ODE, the computation in the loss function. So to avoid that, what we do is that we start to consider some conditional setup. Then basically the data distribution can be considered some kind of the analytic form. It's kind of the Gaussian deformulation. Then all the things basically can be defined into the closed formulation. So that's the kind of things in terms of like why we see the conditional setup. But obviously at the end, while we can directly compute the conditional vector field, that's not something that we want, right? We want to basically get the marginal vector field, right? So how are we going to compute the marginal vector field based on the conditional vector field? So I'm going to skip some details here. Actually, if we start to discuss all the details, that will take another 30 minutes. So if I skip some details here, based on like those formulations, actually the marginal vector field can be computed based on the conditional vector field and also the conditional probability path like this. So using this formulation, what we can do is that what we wanted to do in the previous flow matching case was basically to learn the vector field here using the neural net, using this loss function. But based on the previous formulation, what we can do is that we can still learn the marginal vector field, but using the conditional vector field by just sampling the x1 and also the time t. So these two becomes basically the identical. So basically what we can see is that we can consider basically learning the marginal vector field by just computing the conditional vector field. And for this, we did not have the analytic form, but for this, now we have the analytic form, right? So it's just like lot of like, sort of the Monte Carlo kind of things, right? So we basically sample the X1, and based on that, we compute like this, like close from this, and then basically minimize this. Right? So this is kind of like very similar with what we have seen in the score prediction case, the prediction in neural network in the diffusion case. But the thing is that now we basically not learning the score function, but the velocity function. It's like changing the kind of quantity that we are going to learn in the context of the flow matching. So there are some connections between these two in that way. So that's the thing. So we now have the closed form for this. Then you can also see the analogy in terms of like training the diffusion models and the flow models. So in the diffusion model case, we already implemented this, right? What we need to do is sampling the data point x1 and the time step, and then sample the noise there, and then compute the xt, and then basically training the neural network that predicts the noise there, right? It's kind of very similar. The only thing is that instead of like noise, now we basically compute this, right? x1 times the t, and then sample the xt, and then based on that, we conditionally develop d, and then we train the neural net that now predicts this quantity, not this core function. And then after that, the generation process is basically the same. Here we have some complicated formulations in this core, the models, right? Well, it is not actually the complicated. For the VP case, actually, this was also quite simple form. In the flow matching the case, we directly have the notion of the effective field, which means that the generation process becomes that we sample the x0 here and just like compute ODE using any ODE solver that you want to use. And this kind of the ODE formulation has some bunch of the other advantages in terms of the performance and also the acceleration as well. So at the beginning of like this lecture, I mentioned some kind of the ideas in terms of like how we can further accelerate the generation process through the fine tuning, right? Using the flow models, we're gonna also see some very simple, surprisingly simple, quite but effective the ideas in terms of how we can also accelerate this kind of the generation process with the flow models. But even before that, you can see that, so you can see the meaning of like with diffusion and with the OT here basically means that this is the case like we are defining the mu and the sigma function in a way that matches the full process of the diffusion models. And this is the case that we are basically defining the mu and the sigma function as the straight to the trajectory. So by simply changing the part, you can see that we can achieve some kind of the improvement over some kind of the results like this, which means that we didn't need to make some kind of some curvy the trajectory with the diffusion models. Just make it everything kind of straight. But here also one small thing is that we are making the conditional trajectory to be straight. But after training all the things with the conditional trajectory, it does not guarantee that we're going to have some straight trajectory, the marginal the trajectories after all the training. So yeah, we're going to get into that because everything is expected value, right? So we're going to get into that, why we may see some kind of still banded trajectory after the training, and how we can also fix that still some kind of the fine tuning. So that's the idea that we are going to discuss next time. Any questions on this? Did you now get the idea in terms of how we can solve the problem 5, the last test? Okay, so let's continue discussing flow matching next Monday.